Alrighty, in this video I'm going to do number 4, then pages 10 and 11 so that it finishes up everything in this lesson here. For number 4, it is asking us to find the value of t if the speed of the particle is 24 given your two parametric equations. So you know that the formula for speed is the square root of your derivatives. And then we just got to find the derivative of x with respect to t and y with respect to t. So dx dt is going to be 6t, dy dt is going to be 2. And then if I square it, then I know that dx dt squared is going to be 36t squared. And then t squared is going to be 4. We know that the speed of the particle is 24. And then we just got to solve for t. Now, if you don't know what 24 squared is, that's okay. You could just leave it as 24 squared. The AP readers will be happy because at least you know how to solve a simple equation. And then if you solve for t, you'll get plus or minus, but because it tells you that t is greater than 0, I'm using the positive counterpart. So whatever value this is right here. All right, and then looking at number 5 here, she looks messy because there's a lot of work that needs to be done here, and that's because you kind of need two things. They give you y is equal to x squared plus 1, and they give you the speed. They tell you that dx dt is negative, and we need to figure out what dy dt is at the point 2, 5. Now, that's a lot to work with, but we just need to break this down step by step. You need every single thing. So whenever you're doing an FRQ or you're doing an MCQ, and you didn't use everything, then something's probably wrong. So the first thing that I'm going to look at is y is equal to x squared plus 1. Now, whenever I think about y is equal to x squared plus 1, and I think about what I know about parametrics, I'm going to think about, maybe I should just take the derivative of this. Taking the derivative of this is just 2x. And then you think, dy dx is the same thing as dy dt over dx dt. And then you're going to think, speed. If I'm thinking about speed, then my formula for that is going to be the square root of x prime t squared plus y prime t squared. Dx dt is less than 0. And then we need to figure what dy dt is at the point 2, 5. Now, if I'm using the point 2, 5, where 2 is x, and I plug in into this right here, so this is where I'm using this now. If I'm going to plug in 2 here, notice how that's 4, okay, which is a positive number. So now we're going to use this information because it's telling me that dx dt is less than 0, which is negative. Now, if I know that dy dx is positive based off of this information in blue, and I know that this right here is negative, then I also know that dy dt needs to be negative because dy dt being negative over dx dt being negative makes a positive derivative value at x is equal to 2. So that tells me that dy dt is also negative. Okay, so not a lot of things to work with. I'm gonna go ahead and replace that to be root 2. So not a lot of things to work with here, but what we do know here is that if I were to probably look at this, I could probably remove the square root symbol. And then I have x power t squared plus y power t squared. Okay. Now, also, I already know what my derivative is at 2, so I could say that at 2 dy dx when x is 2 is 4. So this means that dy dt over dxct at 2 is also 4. Now this is going to help us a little bit because we have 4 is equal to dy dt over dxdt, and then we have 2 is equal to dxdt square plus dy dt square. All right, so we're going to solve this using systems of equations, and what I'm not trying to do is solve for dxdt or dy dt here because those are already squares. So what I'm going to do is solve for dxdt or dy dt here. Now, to make my life simpler, and because I want to solve for dy dt, I'm going to go ahead and solve for dxdt here so that it's in terms of dy dt. That way I could just replace this and then call it a day. So that's going to give me dxdt is equal to dy dt over 4. And this right here, I'm going to sub that into this right here. So now I have 2 is equal to dy dt over 4 square plus dy dt square. If I simplify her down a little bit, I'm going to get dy dt square 1 over 16 plus dy dt square, which means that I am going to get 17 over 16 dy dt square, and then I'm solving for dy dt. So that's going to give me 32 over 17 is equal to dy dt square. And then if I were to solve this, that's going to give me root 32 over 17. We need to have a plus or a minus, but we saw that a couple minutes ago that dy dt is less than 0, which means that we should have a negative value here. Isn't that crazy? Number 5 is a really good problem because it tests your skills of using your knowledge of dy dx being dy dt over dxct, and it also uses your knowledge of the speed formula. Crazy. All right, for number 6, we have a particle moving along a curve in the xy plane for time t is greater than or equal to 0. dxdt is that lovely thing, dy dt is that lovely thing at time t is equal to 1. And we want to find the speed of the particle at t is equal to 1. Now, whenever you're setting up your notation here, please remember to do not use any linkage errors here. So whenever I'm doing this, I want to make sure that this is this right here in terms of my notation. Because if I do this, this means that at any time t, the speed is going to be the same thing as what we have for time t is equal to 1, and we don't want that. So this right here would be a linkage error. That's fine. Now, lucky for us, we don't have to take derivatives because both dxct and dy dt are given to us. So we're going to use our handy dandy calculator and then put this into the calculator here. We are going to do the square root and then alpha trace y1 of 1 square plus alpha trace y2 1 square, and that gives us 6.0509 as my speed. 6.0509. All right, for number 7, we want R to be the region in the first quadrant bounded by the curve described by the parametric equations. X is equal to cosine cubed of t, y is equal to sine cubed of t, and the axes. What is the perimeter of region R? Now, I'm going to be honest, I don't know what this looks like. So, I am going to graph this on parametric mode. We haven't done a lot in terms of parametric mode, but I just wanted you guys to see what this graph looks like if it is in parametric mode. Because remember that with this, your bounds are going to be in terms of t, aka in terms of parametric mode. So we can't just find the intersection and then call it a day and Cartesian points. So if you said pi over 4, well, pi over 4 is in terms of x's and y's. Let's see. So go to mode, click on parametric. You're going to see this right here. And then you're going to type in cosine of x, or cosine of t in this case, to the third, sine of x to the third, graph. This is probably going to be too small for you guys, so I'm going to just go ahead and change my window so that I could probably do zoom fit. Okay, there we go. So notice how here, this is my parametric curve, and I want to find the perimeter of region R. Now, I already know that the region R is bounded in the first quadrant. So whenever I'm looking at this graph right here, I'm looking at this part, I'm looking at this part, and I'm looking at this little curve. Now, based off of the graph that we saw here, we know that our height is going to be 1, and our length is going to be 1. So this is 1, and this is 1 here. So I know that I have 2 right now. Now, in addition to this, you'll notice that whenever we find the bounds in terms of t, and I trace this, and I go to 0, notice how it starts at 1, 0, and then as I move to the right very slowly, I'll eventually hit 0, 1. Probably. I don't know. I don't know if I am. But eventually, what's going to happen is it's pi over 2. 1.57. And that should make sense because if you think about it in terms of the unit circle, quadrant 1 is bounded by 0 and pi over 2. Now remember that your arc length formula is going to be from 0 to pi over 2 dx dt square plus dy dt square, and then dt. All right. I can't really do this on parametric mode, so I'm gonna actually convert this back into function mode so that I could plug in a cosine and sine, because unfortunately, unlike the previous problem, we need to take the derivative of this. That's not going to be fun. So we have math 9, 0 to pi over 2. And then we have, okay. So then we have nth derivative of 1 at x is equal to x. Yep. Now I gotta square this. So how the heck am I gonna do that? Oop, Jesus. Let me actually do that now. Okay, there we go. And then math. Oh, Jesus. Math 8. Trace y1, x is equal to x. And then, oops. Math 8 again. Alpha trace y2. X is equal to x, and hopefully this works. I don't like that answer. Anyways, it should have been 3/2, and then you add the 2. So that gives us 3.5. Which means that I probably did something very silly goofy in terms of, oh, that's because I didn't take the square root. Great. So now, taking the square roots of everything by raising everything to 0.5, there we go, 3/2, 1.5. Oops. So then you get 1.5 there, and then add 2 to get your final answer of 3.5 for the perimeter of region R. All right. Going from 8 and 9, which is more calc stuff. This shouldn't be too bad now, hopefully. For part A, it's asking you to find the acceleration vector at time t is equal to 1. So what you're going to do here is just take the derivative of the velocity at time t is equal to 1 and then see what you get. So let's see, we have t 1 plus t squared, and then 2/t. Now, theoretically, we could just use the, we could do this by hand, but I'm not trying to do that. Oh, great, I have an add. I don't care about this. Anyways, what was I doing? Oh, yep. Alpha trace y1 at 1. And then alpha trace y2. Great. Trace y2 at 1. So then we get 0, and then we get -2. Crazy work. And then it says, if the position vector of the particle at time t is equal to 1 is this little thing right here, find the position vector at time t is equal to 2. Okay, so because we want to find the position vector, right? We are going to use vector notation, obviously. So for x of 2 here, that is going to be ln of 2 over 2, because that's my starting point, plus the integral from 1 to 2 of x prime of t dt. And then to find y of 2, that's going to be 2 plus the integral of 1 to 2 of y prime of t dt. So then we are going to do that in our handy dandy calculator by doing ln of 2 over 2 plus the integral from 1 to 2 of dx dt. And that gives us 0.8047. And then you're going to do the same thing for dy dt. So we're going to do 2 plus the integral from 1 to 2 alpha trace y2. That gives us 3.386. Meaning that our position vector at time t is equal to 2 here, x2, y2, is going to be 0.8047, 3.3862. Okay, so one important thing to note is that because it asks us the position vector, I want my notation as a vector. So notation does matter. In this case, we're not using parentheses unless it tells you that it's a, coordinate. So like 9b, it says find the coordinates of p, so you're going to use parentheses. 9 is the same thing. I'm not going to really do it because it's the same thing as 8 in terms of 9a and 9b. I'll probably do 9c just because it's the equation of the tangent line again. So to find the equation of the tangent line, you need dy dx. Now in order to get dy dx, you need dy dt over dx dt, which we already have. So we are going to put that into the calculator, figure out what that is at time t is equal to 2, and then see what happens. Actually, I can't do that. I kind of need part B, because it says find the equation of the line tangent to the curve at P. And we do not know what the coordinates of P is. But you would do dy dx is equal to dy dt over dx dt for t is equal to 2. And then you would do y minus y2 is equal to dy dx at time t is equal to 2, and then you'll do x minus x2, figuring out what x2 is and what y2 is based off of part B, which I'm not going to do, but you guys can look in the student on Twitter, obviously. All right, so last one, number 10, it's a calculator interactive problem. It's asking you for what values of t is the particle at rest. Now remember that the particle is at rest when both dx dt and dy dt are at 0. So I'm just going to plug in, well, not plug in, but I'm just going to take the derivative of this and then see what happens whenever I do that. Set this equal to 0. And then set this equal to 0. I'm going to solve this, so I'm going to have 3t squared minus t minus 6. And that's going to give me t minus 3, t plus 2, t is equal to 3, t is equal to negative 2. And then same thing here, if I take out a 3, and then that gives us t minus 1, t minus 3, which gives us t is equal to 1, and then t is equal to 3. And then that tells me that at time t is equal to 3, my particle is at rest. All right. Hopefully that helped in terms of these last 2 pages in the packet for 10 and 11. And then you'll do page 12 for homework, and then we will start FRQs.